apply still to other data sets than transcriptomics. So there's really a lot of discussion still in the literature, and some fields need to set this parameter differently than other fields and so on. So I wanted to make a kind of a side note and tell you a little bit about my research and how it might connect with t-SNE and how it might help maybe tune those hyperparameters. So in my PhD, we've developed this cost function. Just don't confuse it with the cost function of t-SNE. We also call this a cost function, but maybe I should call it a metric. So we've developed this metric for assessing the quality of an embedding, the quality of a projection. And I'm going to show you how we constructed that metric and then connect with t-SNE. And maybe that metric could help us to tune the hyperparameters of t-SNE. So now I'm going to show you how we constructed that metric of assessing the embedding quality. So if we have a projection, let's say a two-dimensional projection, so those are just two coordinates, and my projection might look like this. In 3 dimensions, if I viewed that data projection, it looks kind of like a dome. So there's this back wall that you just barely can see, and it has kind of this dome shape in 3 dimensions. So now if I project it onto 2 dimensions, then this back wall that was there in 3 dimensions is sitting right behind kind of that front wall. So this projection onto 2 dimensions from 3 to 2, it generates what we call non-uniqueness, or this overlap of observations. So some observations got projected right on top of each other as we went from 3D to 2D. And if I have some variable, which is that blue color that colors that projection, and I visualize that variable on my projection, then you can see that from the perspective of that variable, from the perspective of that blue color, we get a lot of non-uniqueness. And what I mean by that is that there are some regions on that projection that if we were to, let's say, train a machine learning model to predict the blue color, then it would really be mixed up and it wouldn't know which value it should predict. So for example, over here, we get over a very short distance, we get both a dark blue color and a light blue color. So there's kind of this uncertainty now that we introduced through projection, that if we train a machine learning model, it will not be able to tell, should I predict this light blue color or the dark blue color, because they're just right on top of each other. And that is particularly problematic for modeling purposes. So this is where I was kind of coming from, using projections for modeling data sets. But later it can also be used for using projections for visualization. So in techniques like t-SNE. And the starting point for building our metric was the work done by my colleagues. And they developed this earlier metric, which is called a normalized variance derivative. And how that metric works, what we're doing to compute that metric is we're now scanning that projection for variation in that blue color, whatever that variable is. It could, for example, be temperature in combustion science, or it could be a gene expression in biomedical data. As long as you have some numerical value, you can scan that projection and compute the variation in that variable over the projection, but we compute it under a certain filter width. So in this case, I'm scanning that projection at those big length scales with a big filter that is, the radius maybe is of the order of the whole projection. But later, we're going to shrink that filter and scan that projection at smaller and smaller filter widths. But if I scan it at those big length scales, so with a filter that is, looks like this, it's a reasonably big filter. If I see variation in that blue variable under that filter, then I will get this first peak in this d hat profile. So that's the metric that my colleagues developed. And this is how it's being constructed. We're scanning it, we're measuring the variation in a variable. And if there is variation, then that will create this raise in the d hat profile. And in this case, when I'm scanning it at those big length scales, I see variation in the blue color under that filter. Even within the area that I have visualized over here, my variable goes from like light blue over here to darker blue over here. So there is some variation that I'm detecting at those biggest length scales. And that variation is determined with this equation. So phi would be just the actual value of my variable at a given point, and k, which is a function of sigma, that's the kernel, and it's still a Gaussian kernel. So just like you saw in t-SNE, and that's kind of the same notion. We use a Gaussian kernel to approximate that variable under that filter width. So Gaussian kernels are used all over the place for all sorts of different purposes in data science and machine learning, and that's just why it's also being used over here. And then we also normalize that variance by the value of the variable at a given point minus its arithmetic average, just a plain arithmetic average. It's not important that you understand that equation at this point. I just wanted to give you some context that these scanning is performed again with Gaussian kernels. So we can now start scanning that same projection at smaller length scales. So we zoom in on every region on that projection, and we start scanning it with a smaller filter. And we change those filter sizes, so the sigma, we change them continuously. And you can see that on the x-axis here, they really span a couple of orders of magnitude in their size. So we go from like 10 to minus 1, so 10, then 1, 10 to minus 1, and all the way to 10 to minus 4, or we might even go smaller than that. So we span a couple of orders of magnitude in the types of filters that we use. But let's say at this kind of range of scales, maybe those filters are of the size somewhere between 10 to minus 2, 10 to minus 1. So there's a couple of them. Maybe we take 10 different filters in that range. We scan the projection. And if I still see variation in my blue variable under that filter, then that will give me another raise in this d hat profile. And in this case, I still see variation in that blue variable because partly because there's this overlap problem. There's these observations that got collapsed right on top of each other, and they create a lot of variation, right? Because on very small length scales, you can mix up the dark blue and the light blue data points over a very small length scale. So that creates a lot of variation under even very small filter widths. But even without the overlap, probably you would still detect some level of variation in that blue variable at those length scales because, for example, if you look at this region over here, there's still some difference in the shade of that blue color over that length scale. And then we basically keep going. We scan that projection over even smaller length scales. So now we go to really small length scales. We zoom in on that region, for example. We start scanning it there. And in this case, I'm still seeing a lot of variation. And that is especially because of that overlap problem. So if I go into all of that region where the overlap happens, I'm getting, dark blue observations mixed up over very small length scales with the light blue observations. And that creates a lot of variation still. So I'm seeing another kind of peak in that d-hat profile. And at some point, if I kept going and scan it at really, really small length scales, at some point, my filter, so this circle, is going to be so small that it's just going to encapsulate single data points. And at this point, I will not see variation anymore, right? Because one filter has got just at most one data point inside. And that does not create a variation in that blue variable. So at some point, once we go really small with the length scales, this d-hat is going to be 0. It's just going to be quiet at this point. Okay, so this was the starting point for constructing our metric. Remember that we want to have a metric that gives us the quality of a projection. What is the quality of the embedding? In some sense, in the sense of those, overlaps on a projection. And now our cost function, so that final numerical metric that we constructed, and don't mix up this with the cost function of t-SNE, it starts with that d-hat profile. So we first construct this profile, which collects the variation over different length scales. And then it penalizes that profile in some way. So we start with the d-hat profile, we penalize it in some way, which means we multiply it by some function. And don't worry about the exact equation for that function. Just think of this dashed box as that's some function that we multiply this d-hat profile with. And once we multiply it, we get this. So we get this resulting curve that looks slightly different from the original one. And especially, it kind of amplifies this variation that happened for very small length scales. And there's some rationale behind that for why we penalize that variation at very small length scales. And the reason for this is that those can particularly be linked to non-uniqueness, so that overlap problem on a projection. Typically, when overlap happens, it will generate a lot of variation for very small length scales, far away from those biggest length scales. And there's also another term in that penalty function which rewards large feature sizes. So what do I mean by that? Well, the location of that rightmost peak, so the peak most for the biggest length scales, wherever that peak happens, it indicates what are the kind of big scale variations over the embedding, over the projection. And we want to typically have them as big as possible, because if we go into modeling, then it's just easier to predict variable from an embedding if it has a smooth variation over the projection. So those are kind of the largest feature sizes. And now the last step that we do is we compute the area under that curve. And that's it. So this integration from the smallest length scales to the largest length scales, those are the bounds of the integration. And that computes the area under that curve. And now that we get an area, this is just a number. This is a single numerical value. And what that gives us now is for a given projection, And for a given variable, that blue color, we can take different ones, different kind of sets of colors. But for a given projection and a given variable, we get a number, a numerical value for how well is that particular variable represented over the projection. And if the projection is well behaved, you'll get a smaller number. If it's poorly behaved and has some problems, you will get a higher number. So just to give you a comparison, how would that d-hat profile look like if we have a very good projection that did not have this problem of overlap? And here's one projection like that. So this one is really well behaved. It doesn't have that problem of overlapping observations. Still a two-dimensional projection. And if I compute the d-hat profile for that particular projection, it will look something like this. So it will only have a single peak for the largest feature sizes, and then it would be quiet. It would be 0. And the reason for this is that as we start scanning that projection over those big length scales that are, of the order of the size of this whole projection, then we start to pick up some variation. Even, over here under that circle, you can see that that the blue color changes from light blue to dark blue. So we start to pick up some variation in that variable under that filter size. And then we start scanning it for smaller length scales. We take smaller filter sizes. So maybe we zoom in over that region. We scan it there. And at this point, we're still seeing some variation. And that might manifest, let's say, as a raise in that profile somewhere over here. So for example, under that filter, you can still detect some variation. It goes from lighter blue over here to darker blue over here. But then as I keep going and I keep scanning that projection at smaller and smaller length scales, I'm not really seeing any more variation, or not much at all, because this projection is well behaved, and at some point my filter is so small that I'm really only looking at small, neighborhood of every data point, and this blue variable just does not change so sharply to create variation at such a small length scales. So in this case, under that filter, really what you're seeing inside of that circle is just a light blue color. So that has almost no variation. And this is because this d-hat profile is now 0. So you're not detecting any variation. So that's kind of a profile that you would get for a well-behaved projection. And then you would apply the same kind of principle to create our numerical metric. So I would take that profile, multiply it by my penalty function, which returns this curve now. We give it some reward for the largest feature size. And there's, because the d-hat was 0 over here, there's no, amplification as big as what you saw before. And then we compute the area under that curve, and we get some number in that way. So that area gives us some number. Now, if you compare this with the area for that problematic projection, then this was a much bigger area, right? Because there was this variation for very small scales, which get amplified, and then that creates a lot of area under that dashed curve. Not nearly as much for this curve for a good projection. So now, just to give you a number, once I compute our numerical metric for this problematic projection, which had overlap due to this back wall that was there in 3D, we get 5.1. And if I compute it for this well-behaved projection, I get 1.1. So much smaller area for a well-behaved projection than for a problematic projection. And here I should note that this cost, what we call this number a cost for a given projection, this cost is always in relation to some quantity of interest, some variable. In this case, it was that blue color, but I could potentially take a couple of variables to look at because different variables might have a different distribution over the projection. I could take a couple of those and compute, let's say 5 or 6 different costs, and then maybe take some average over them and have like a general average assessment of my projection, of my embedding quality. And in the original publication, we demonstrated a couple of applications of this metric to different data sets. So for example, combustion data set, this is the area where me and Professor Parenta work on, so combustion, numerical and experimental combustion. And for example, here's a 3-dimensional projection, the same one in these 2 images. That's the same projection, the same embedding, but just colored with 2 different variables. So in this case, I color it with the mass fraction of hydrogen, which is a fuel in that combustion setting. And in this case, I color it with temperature. So the temperature is low where no combustion is happening, and then it's really high where there's most of the combustion happening. So same embedding, you see that the shape of this projection is the same in those 2 cases, just 2 different variables. And now I'm assessing with our metric, how well is that variable represented over that same projection. And you can see that the hydrogen mass fraction creates this, sharp changes in a value over very small length scales on a projection. So over here, you can see if I zoom in on that region, you can see that the hydrogen mass fraction changes from 0, those are those blue trajectories, blue points. It changes from 0 to 1 really sharply, or almost 1 over here and 1 over here, over very small distances on a projection. And that would typically raise that d-hat profile for small length scales. So you're creating this really small feature on that projection. And that increases the cost compared to the temperature, which does not experience such sharp variations over the projection. So you can see the temperature is developing pretty smoothly over that projection. It does not create such high gradients over a projection. So the cost for temperature is lower than the cost for this hydrogen mass fraction. And this is also kind of gives you the benefit of assessing the same projection, but with different variables, because some variables might be better at exposing some problematic behaviors on a projection. And in this case, it simply happened because the projection technique, which was PCA in this case, it just collapsed those 2 regions, one region corresponding to mass fraction being 1 and one region corresponding to it being 0. It just collapsed them onto a similar region in the projected space. So we also showed some examples with atmospheric pollutant dispersion and how the cost function could be used there. We could, for example, look at the turbulent Schmidt number, which is an important variable when it comes to atmospheric pollutant dispersion. And those, again, are PCA projections, 2-dimensional PCA projections of the same data set. The only thing I changed is how I scaled the data set before I computed PCA. And you can see that just scaling the data can really alter the PCA projection quite a lot. So for example, this projection, if we color it by this turbulent Schmidt number, that color again develops kind of smoothly across that projection. It goes from highest values to lowest values pretty smoothly over that projection. But here for this PCA projection, you really mashed a lot of the observations one on top of each other. And this is just by changing how I scale the data before I do PCA. And again, our cost function, our metric picks up that a lot of variation, maybe non-uniqueness even. It picks that up and it creates a higher cost than for a well-behaved projection. And then you can even create something like rankings of different projections with this metric. So we show that on this argon plasma data set, where you can look at the temperature of electrons. And I could, for example, scale my data set differently. So those are the names of different scaling options that I could apply to my data before I do PCA. And we could even look at, how do the cost value changes if we change the dimensionality of the projection. And the nice thing about our metric is that you can compute it for any dimensionality, 2D, 3D, 4D, 5D, and so on, anything. So for example, 2D projections usually have a higher cost than 3D projection and 3D projections. And that kind of makes sense, because once you go from 3D to 2D, you're collapsing more of the data points. So there's a higher chance that you will create that overlap once you go from 3D to 2D. And then 3D, they're associated with smaller costs for really all of these scaling criteria that we tested. So anyway, I want to go back to t-SNE now. And I wanted to give you that kind of introduction because I wanted to now show you that maybe our metric could help us in tuning those t-SNE hyperparameters, like perplexity, for example. So can our cost function help in assessing, how good is a given t-SNE embedding? So that's a first funny example. I computed the cost for these two embeddings coming from t-SNE. That was perplexity equal to 1, and that was perplexity equal to 30. And you can see that the cost is higher for the perplexity 1 than for the perplexity 30. It's smaller over here. And the reason why it's higher here is that there's kind of more variation in that blue color again over the projection. So for example, if you look at a region like over here, you have this darker blue, which sits close to this lighter blue, and maybe right near them there's this dark blue color. So once I scan my projection, my embedding with a filter that's kind of encapsulating those data points, I will see a lot of variation. For example, over here in that region, and that will kind of amplify that d-hat profile, and then it will create more area under that curve and so on. But if we look at this projection, then the blue color varies kind of smoothly over that projection. It's nowhere near that sharp of a variation across this embedding as it was here. So there's a pretty smooth variation in that blue color. And if I have a small filter and I scan this embedding with my small filter, then maybe for any location on that embedding, I will not see much variation. So this is kind of the reason why, this kind of thread-like structure in the t-SNE embedding creates a higher cost. And our metric pays attention to these feature sizes. So if there's different feature sizes at very small length scales, it would pick that up. Now, I also computed this for that handwritten digits data set. So this was the PCA projection in 2 dimensions. And you see that it just mashed all the points, all the classes together, and the cost is high. It's higher than for the t-SNE projection. And it's because, again, of that overlap of observations. So you really overlap all of those classes over each other. And t-SNE is much better, at spreading those classes over that 2-dimensional space, and the cost associated with that is smaller than for the PCA projection, because again, any filter you take, you simply get lower amounts of variation over a small filter. So our cost function pays attention to that non-uniqueness generated on an embedding, which can come from overlapping observations. If there's an overlap and also the variable you're looking at changes value across that overlap, then you're generating non-uniqueness. So now I took this toy data set, and it's just a 2-dimensional grid, a square grid. And I will do kind of a similar exercise as before. So I take a 2-dimensional grid like this, and I embed it into 2 dimensions with t-SNE. So that's, of course, no gain in terms of dimensionality reduction, but it's just to see what t-SNE can come up with in terms of embedding this into 2 dimensions. And I also colored that grid by this kind of circular feature. So that's again coming from like a Gaussian distribution over that 2-dimensional data set. So I created a whole bunch of embeddings with t-SNE of that 2-dimensional grid, changing the perplexity. So you see it goes from 1 to 16 in this case. So you get all the numbers of perplexity. And here I'm showing you what the actual embedding looked like with a given perplexity number. In this case, you see that even for perplexity 1, we get a pretty good kind of still global structure of that grid, of that original grid. So we do not get these threads like we did for that earlier data set. So that also kind of can show you that for different data sets, those hyperparameters might work differently. And this also kind of suggests that for a given data set, you should optimize for that perplexity parameter specifically. And settings might not carry over between data sets. And for each of these embeddings that I created, I'm computing the metric, our numerical metric for how good of a quality that embedding is. And you can see that, for example, the highest costs. So, okay, the highest cost happened over here when this embedding is really fragmented into different regions. And then you can see that once I increase the perplexity beyond something like 5, so I go to 6, 7, and so on, the cost is pretty much the same. And that's just because the embedding doesn't change very much. It's that 2-dimensional grid structure. But then we went to perplexity 15, and you can see that this flipping of a corner happened. And now the cost jumped a little bit to reflect that. And the reason for that is that our metric picks up this distortion and variance of that variable that colors this embedding. So it's that it's that Gaussian feature that goes from yellow to purple. That was my variable that I looked at in this exercise. And you can see that if I were to scan this embedding with a filter that has got this size, then I would pick a lot of variation over here, because my values go from purple to yellow over a reasonably small filter size. But if I have a nicely behaved two-dimensional grid and I scan that with my filter, then over here I'm not experiencing nearly as much variation. It goes from maybe orange or slightly red to orange, and it's just not picking up that much variation as it is over here. So higher variation in that variable over here, that's what created that increase in the cost value. And it's because of that flipping of the corner. So the cost function could help us in some cases to determine the quality of a t-SNE embedding. The question is always, what variables do you look at, and what are your important variables that you want to have well preserved on your t-SNE embedding? And for some sciences, like biomedical sciences, there might be a straightforward answer. Okay, I want to look at this particular variable, let's say gene expressions, because I'm mostly interested in that. And then researchers could tune this perplexity parameter such that they have the best embedding from the perspective of, let's say, gene expression as a variable. So this is everything that I had for you today. I will give you some summary about t-SNE, some high level points to remember. So the strengths of t-SNE is that it's pretty powerful for data visualization. So you could see that when I compared it to PCA, it often did a much better job at separating different classes in the data set. And the powerful thing about t-SNE is that it can work even for very high dimensional data sets. So those biomedical data sets that might have thousands of dimensions originally, people collapse them onto 2 dimensions, and they see some physically meaningful patterns that emerge. And in particular, t-SNE is good if you have distinct clusters in your data. So it's good for categorical data sets. And especially it can be interesting when you have this hierarchical organization in the data. So you have, let's say, like for the mouse neocortex data set, you had this high level description of the cells. So you had excitatory neurons, inhibitory, and non-neuronal cells. That's kind of the high level hierarchical organization of the data. But then once you go into each one of these, you have a finer organization in the classes, and you have some individual gene expressions. And t-SNE can be good at separating those into different regions on your lower dimensional embedding. And t-SNE creates structure at multiple scales. So depending on that perplexity parameter, you can force it to, let's say, pay attention just to the nearest neighborhood, or pay attention to larger neighborhoods. So you can create that structure at multiple scales. And of course, many of those t-SNE projections look really beautiful. So you can decorate your house with t-SNE maps, even for like toy data sets, like this 3-dimensional surface, you already can get a pretty picture, especially when perplexity is low. It creates this fine threads, which look really interesting. Now, there are some weaknesses of t-SNE. So first of all, the topology of that embedding is strongly dependent on the hyperparameters, and also initialization. We didn't talk about that, but how you initialize the t-SNE method, that also can play a role. Whether you do that randomly or initialize with PCA, that can push those data points in different ways. But especially that parameter perplexity, it affects how the embedding looks like quite a lot. Now, t-SNE can get stuck in bad local minimum. So it's under the hood. It's using that cost function that has this attraction and repulsion. And this is being performed with gradient descent to minimize that cost function. And that is always prone to be stuck in a bad local minimum. And you've seen those examples where a single data point was either pushed outside of the data set, and at this point, the mechanics of t-SNE is stuck. It just cannot get past that, or a point can be trapped inside of the data set where it doesn't belong. And at this point, there's not much more that you can do about it. It's just stuck there. And then another thing to remember about t-SNE is that those embeddings, those projections, they're computed by solving this optimization problem. So we're minimizing that cost function that describes those probabilities of neighborhoods. And because it's solved through this optimization, using gradient descent to minimize that cost function, you don't really get a mapping function like you do with PCA. So if you do PCA on a data set, you have your eigenvectors, and then you can project any new sample onto the same eigenvectors and get a projection of samples that you haven't used before. But with t-SNE, you can't do that. You just have to give it the whole data set. It runs that optimization on that data set. And as a result, you get a map, you get this embedding, but you don't get a mapping function. So if you have now, let's say, a new patient arriving, and you want to see where that patient would fall on the t-SNE map, then you can't do that. Well, actually, there are some techniques being developed in research to help us do that. But by default, this optimization that t-SNE does not give us a mapping function like we do with PCA. So we can't project any new data point. And if you have a new data point or a new sets of points, let's say you have 1,000 new patients, you simply have to rerun the optimization again with that new point or those new points, and now see how those points, where do they land after a new optimization. So finally, there's this interesting quote that comes from Terry Pratchett, and I think it fits into many of the machine learning algorithms, and especially t-SNE. So there's this book where there was this robot, and that's a quote about this robot. So provided that everything in the kitchen was very carefully positioned, the thing could sweep the floor and make a passable cup of tea. If everything wasn't carefully positioned, it'd strip the plaster of the walls and make a furious cup of cat. So it's kind of, describes well a lot of those machine learning algorithms, that sometimes you have to set things just right for them to work well and work to your advantage. So like that perplexity parameter. But if you don't set it right, then you might get a really misleading answer. So that's everything I had for you today. And if you have questions, I'll be happy to answer. And you'll have the recording of the talk. There's no coding examples today, but if you want to run t-SNE, then scikit-learn contains the function for running t-SNE.